Welcome you all for another beautiful presentation on electronic devices and circuits. Today we are going to see another very important biasing configuration of transistor, that is self-bias configuration of a transistor. The self-bias can also be called as with various names like emitter bias and universal bias and voltage divider bias. These are the various names that are being applied for this particular configuration. So far, if you refer our previous presentations, we have covered two more important biasing configuration of transistor. Those are fixed bias configuration and the second one is collector to base bias configurations. In fixed bias configuration, we have seen that the stability factor S is equal to 1 plus beta, because the stability factor is more, right? So the value of the stability factor must be as minimum as equal to 1. If the stability factor is 1, then you can say that the biasing is very perfect, means the transistor configuration will be working as a good amplifier circuit. There you will get good output and the distortionless output you will get at the output. That is why that is the drawback of a fixed bias. And afterwards we have seen the another improved version of that fixed bias, that is nothing but collector to base bias, in which we have connected the feedback resistor from the collector point to the base. That is what the RB is connected between collector point to the base. Thereby the stability factor will be improved. Okay, that we have seen in the mathematical expression of that particular. You can you can get a very a good thing if you refer that video. And then in today's presentation, let us discuss about the third and very important configuration, that is self-bias configuration or emitter bias configuration, or also called as universal bias configuration and also called as voltage divider bias configuration. And this is one of the most important configuration even than the fixed bias as well as the collector to base bias configurations, right? Let us go into the circuit configuration of the transistor and we will see how the stability factor is derived for this, self-bias configuration, right? Let us see the expression part of it. So let us see the circuit diagram of a self-bias configuration of a transistor, right? So this is the circuit diagram of a transistor which is configured in self-bias, or this circuit diagram is also called as emitter bias and also called as universal bias and also called as voltage divider bias. Okay, so this is the transistor. If you can see, this is the transistor, this is the emitter terminal actually, and this is the base. As you already know, this is the collector terminal, right? So here at this base, if you see R1 and R2, these are the two resistors connected at this particular point in parallel combination. Whereas if you see at this particular collector terminal, the collector resistor will be there, and at this collector point we are taking out the output, okay, output voltage with respect to ground. What is this actually? It is common emitter amplifier obviously. Therefore emitter terminal, at emitter terminal you have the emitter resistance RE, and this emitter is grounded actually with respect to R2, right? So this is the, and then this R1 as well as RC, if you see that these two are joined together and they are given to the plus VCC supply voltage. This is called supply voltage, and this is the biasing resistors R1 and R2, RC and RE. These are the external resistors. These are called biasing resistors, and plus VCC is called as biasing voltage, right? I already given that a nice definition for biasing is that, so it is the selection of proper supply voltage as well as the external resistors are called as biasing. Actually, it is the selecting of or selection of proper values for resistances as well as the supply voltage, that is called biasing, in such a way that you will get the proper desired output, and moreover you can say that the distortionless output, right? Therefore, this is the very simple circuit which is to be used under this very important configuration, right? Okay, now what we have to do to find out the stability factor of this particular configuration? We have to find out the stability factor. I already given you the very generic expression for stability factor, right? What is the stability factor? The stability factor S is equal to, what is the formula that we have seen? It is 1 plus beta times by 1 minus beta into, it is dou times IB by dou times IC. This is what the expression for S. Always you have to remember, very, very important formula. Whatever may be the configuration, it could be either fixed bias or collector to base bias or even to the self bias. This is only the direct expression which is to be used to find out the stability factor of given circuit diagram. Therefore, remember this very important formula, 1 plus beta by 1 minus beta into dou IB by dou IC. And further, if you see very clearly this particular expression, what is the very much important thing that we should derive? We should know beta is constant, means 1 plus beta. So, with beta you are nothing to do. Okay, 1 minus beta here dou IB by dou IC. This is what my important thing. I have to find out the value of dou IB by dou IC. Then I have to substitute the dou IB by dou IC in this expression. There I can easily get the value of S. So, my target in this, from this circuit is that to find out dou IB by dou IC. For that, what I need to do? I must write the expression for IB and I must differentiate that IB with respect to IC. That is what my aim in this particular configuration. For that, as I already clearly explained in my previous videos, that remember that, so for the given circuit diagram, whatever may be the bias, so you have to apply the KVL's Kirchhoff voltage law at the input side of the transistor as well as the output side of the transistor, right? Most of the time you can apply the KVL at the input side. By applying KVL at the input side, you will get the IB, because the IB is the current which flows through this base terminal. Actually, IB is the current which flows through this base terminal of the transistor. In fact, IB is your input current, base current. Emitter is grounded. However, your IC is the collector current, is it not? IC is the collector current. Clear? IC is the collector current. Therefore, IB is the input current, IC is the collector current. IA flows emitter current and flows, it is grounded. Therefore, there is no use of about this IA, not required. Therefore, where is IB? At input side. So, now KVL is to be applied. By applying KVL, right? By applying KVL means Kirchhoff voltage law at input side of the transistor. Where? At the input side of the transistor. I can write transistor as T by R. So, what is the input side of the transistor? So, I can note down in this circuit diagram clearly. So, my input loop is like this. My input loop starts from plus VCC here, and it comes to this actually, and it comes to R1 and then R2, and from here directly it goes to this base to emitter, and finally it comes to here, ground point. This is what the flow of voltage actually. Okay, now let us clearly see that here this flow must be taken in this way. Here if you consider at this point, we have one nodal point here. Therefore, at this nodal point, this is what the input side of the transistor. This is what the input side of the transistor. Then what is the output side? Output side is nothing but again from plus VCC, you can come in this way towards your RC and through this VCE and through this emitter resistor RE. This is what output loop actually. So plus VCC, then through RC, through VCE and emitter resistor RE. Because this emitter resistor RE is common for both input as well as the output loops. Clear? RE will be there in both the loops actually, at input side as well as at output side. Clear? Now remember that one important thing that I am going to discuss now. At this particular, as we have two resistors in parallel combination at this particular point B, then the input side of the transistor, this is what the input side actually, plus VCC R1 through R2. This is what input side of transistor. This is to be simplified by using Thevenins law, Thevenins rule or Thevenins theorem. I think you could have been studied in your network analysis, right? What is Thevenins theorem? What is the Thevenins theorem? So, any given linear circuit is simplified in such a way that the voltage source is connected in series with a resistance. That is what the Thevenins theorem. According to your Thevenins theorem, what Thevenins theorem says that? So, the voltage source means V Thevenins, you can call it as V Thevenins, must be in series with R Thevenins. This is what? R Thevenins. This is the Thevenins resistance, this is the Thevenin voltage. So, in the given linear circuit, so if you have a number of resistances, then the resistance will be simplified in such a way that from those resistances you should get the equivalent resistance or Thevenin's resistance. Okay, so in series with this Thevenin's voltage, right? Likewise we have to simplify. So means that what? So at this particular point, let us say that I have V Thevenins. I have to find out V Thevenins. Okay, what is V Thevenins? What is the V Thevenins? Thevenin's voltage, V Thevenins, that is V Thevenins. At this particular point, let us say that voltage will be, let us assume that V is the voltage at this particular point, and that voltage I am calling as VTH, Thevenin's voltage. What is the Thevenin voltage? Nothing but the input voltage VCC into this V Thevenins is nothing but the voltage across the resistance R2. Understood? This V Thevenins is nothing but whatever the voltage I just marked here, that is nothing but voltage across this R2. Therefore, this for this V Thevenins, I am going to find out the V Thevenins value. Therefore, V Thevenins is equal to input voltage is VCC into the resistance where or across which you are going to find out the V Thevenins that you must take. Means that what? It is input voltage means VCC into where I am going to find out the V Thevenins across R2. Therefore, R2 by total resistance R1 plus R2. Therefore, R2 by R1 plus R2. So, this is what my V Thevenins. Therefore, VCC into input voltage into R2 by R1 plus R2. Let us call it as equation number 1. That is my Thevenins voltage. Clear? I think you got it. So, V Thevenins is equal to VCC into R2 by R1 plus R2. Understood? This is what V Thevenins. Then what is RBB? I can call it a RBB. Okay, it is nothing but R Thevenins only, but as far as our configuration is concerned, I am calling it as RBB, or simply you can call it as RB. Nothing wrong in that. Base resistor or RBB, whatever it is, nothing wrong in this. RBB is nothing but equivalent resistance. So, how these two are there at this point? Because between these two resistors, there is a nodal point is there, means with respect to this point R1 R2 are parallel, not in series, because these two are connected here and in such a way that these two are parallel. Therefore what, R1 is parallel with R2, means that what, it is R1 R2 by R1 plus R2. Clear? So this is what my RBB. Now call it as equation number 2. Clear? Understood? Now this particular circuit diagram is further simplified with the help of this Thevenin's voltage and then equivalent Thevenin's resistance. How then this circuit looks like, right? By modifying or by simplifying this particular circuit with the help of these two, Thevenin's voltage and then, now I am going to redraw the same circuit with the help of this Thevenin's voltage. Now I am erasing this for the sake of giving a clear circuit diagram little bit elaborate, right? Let us see how this is going to be. Very simple. There is nothing to feel any difficult. It is very simple. Now let us see, I can draw that circuit like this. So your transistor will be as it is, there is nothing, no difference, and your RE will be there. You can, this is, you can call it as RE only. Now you can make it as ground, nothing wrong, and you will have your RC is as it is, collector resistor will be there, and you will get your plus VC is obviously there. Understood? And now here at this base, this is what my collector, this is what my emitter, and where I have my base. And now what I can have this, this is my RBB, or simply you can call it as R. This is my, this is what my VB, or you can call it as VB. Instead of V Thevenins, you can call it as VB also. Nothing wrong in that, because obviously it is Thevenin's voltage only. But as far as our configuration is concerned, you can call it as so, because the negative point must be grounded to this emitter terminal only. Now this is what from here I am taking as output only. This is the further simplified version. See how simplified the circuit has become. Clear? Now this is what from VB your IB flows like this. Now initially how I have shown from plus VCC, no, from plus VCC like this I have shown. After simplification of this with the help of Thevenin's voltage, now the flow of IB flows like this, and here it is V base to emitter voltage is there, it is plus and then minus, right? Of course here VCE will be there, collector to emitter voltage will be there, plus and then minus, right? So this is what the equivalent circuit. Now this is what the equivalent circuit. Now so this is what your input loop, this is what your input loop. Now this is what your input loop, as well as from plus VCC it is your output loop actually. Now the step 1 you can write. What is the step 1? By applying KVL at input loop, by applying, what is, by applying KVL at input side, at the input side of transistor, input side of transistor. What you will get from this, tell me. So VB is equal to, what is that? VB is equal to, tell me, IB into RB or RBB, whatever you like. If you take VB, then better you can write RB, or VBB, RBB you can write. That is up to you, nothing wrong in that. If you consider VB, then take it as RB. Therefore VB is equal to IB into RB, right? Plus VBE, internal voltage will be there, plus VBE, and then here the emitter is there actually. From emitter, what will be there actually? It is, what is the current flows through? IA, no? IA into RE. IA into RE. This is equation number 1. Equation number 1. And now, because for the for deriving the expression for the stability factor, I don't need the output expression, not required. From the input loop equation only, you can obtain the stability factor, derivation. Therefore, so that I do not require this circuit, therefore I am rearranging this particular. It's not required now, because now this is what a very important equation that which we need. Vb is equal to IBRB plus VBE into, like that, no? Then this implies, where remember that here IE is equal to, in common emitter configuration, IE is equal to, it is the sum of IB plus IC. Always remember, it is the sum of these two. Therefore, this you can call it as equation number 2. Substitute this particular 2 in equation 1. So, substituting equation 2, right? Substituting equation 2 in equation 1. Then what you will get, it is VB is equal to IB into RB plus VBE. Is it not? Plus, what is IE? It is IB plus IC into RE. Clear? So, from this, you can take IB as common here. If you take IB as common, you will get RB plus, here IB is there, no? Therefore, what you will get? RE. You will get RE here. Plus, what else you will get? VBE. Clear? IB. So, we have taken it already. VBE, it is came already. IB into RE. Therefore, IB you are taken as common. Therefore, RE. Therefore, what else is there? IC into RE. IC into RE. Clear? This is what VB is equal to. And from here, this implies what I need actually? I need an expression for IB only. I am solving this expression to find out IB. Therefore, if you write IB, directly I can write IB is equal to, what I will get, IB is equal to, VB already is there, you can write VB. Okay, then bring VBE minus RC, everything you should bring to the left side. Therefore, VB minus VBE minus IC into RE, is it not? By, whole by, what you will get? It is RB plus RE. Am I correct or not? RB plus RE. Am I correct? This is what your IE. This you can call it as equation number 3. Am I correct? Therefore, IB is equal to VB minus VBE minus IC into RE by RB plus RE. Absolutely correct. No doubt at all. Right? Now, what we should do, So, now you got the expression for your IB. Now, differentiate this IB with respect to, now differentiate. What you should do now? Differentiate. Right? Now, differentiate IB with respect to IC. IC. That's what means you are differentiating equation 3 with respect to IC. Therefore, what you will get? Dou IB by dou IC is equal to, that is what the meaning of it. So, dou IB by dou IC, that is what the differentiation of IB with respect to IC means. Then what you will get, VB minus VB. What is VB? It is a voltage, Thevenins voltage, or simply voltage. Voltage is a constant. What is VBE? Base to emitter voltage, that is also voltage. Therefore, voltage. So, this is a constant value actually. So, by if you differentiate the constant value with respect to IC, what you will get? 0 only. Differentiation of constant is a 0. Therefore, you will get 0. Then what actually remains? Minus IC into RE by RB plus RE. Therefore, you will get minus IC into RE. So, in this term, you have IC. Therefore, if you differentiate IB by IC, then your IC becomes 1. Therefore, what you will get, minus RE. You will get, so this becomes 0, VB minus VB part becomes 0, then you will get minus IC into RE only in numerator by RB plus RE. So, as you are differentiating with respect to IC, you will, this IC becomes 1, therefore, minus RE by RB plus RE. This is what your dou IB by dou IC. Clear? This is what your equation number 4. Now, problem is over now. Now substitute this particular dou IB by dou IC in our standard definition of the stability factor. Therefore, substitute this particular equation number 4, nothing but dou IB by dou IC in our stability factor formula. What is the stability factor formula? Yes, is equal to, it is 1 plus beta by 1 minus beta into dou IB by dou IC. This is what my formula. This is equal to, if you substitute this particular dou IB by dou C this much here, then you will get 1 plus beta by what you will get 1 minus beta into what is that? It is minus RE by RB plus RE. And definitely this minus will be becomes plus. It is 1 plus beta by, and definitely it is 1 plus beta times RE by RB plus RE. RB plus RE. So this is what the expression 1 plus beta by 1 plus beta into RE by RB plus RE. Is it not? Then here also, in this case also, as we have assumed in your collector to base bias, here also, if your RB is very less than to RE, is it not? Okay, very less than. If this is the assumption, if RB base resistor is very less than your RE, then RB plus RE approximate to RE. Therefore, RE by RB will get. Therefore, S is equal to 1 plus beta by 1 plus beta by 1 plus beta. Assume that if RB is, or otherwise RE is very much greater than RB, then RB plus RE, the sum of RB plus RE becomes RE. Therefore, RE by RE. Therefore, both will be cancelled out. Then you will get 1 plus beta by 1 plus beta. 1 plus beta by 1 plus beta. Therefore, what you will get, your stability factor is equal to 1 plus beta by 1 plus beta. Okay, so obviously it is equal to 1 if RB is very less than RE. So this is the condition. This is what the stability factor for CE, I mean self bias, or otherwise emitter bias, also called as, this is called as universal bias or voltage divider bias. I think you understood well, and it is good to finish off this particular derivation here, and the little bit elaborate expression that we will see in the next subsequent presentation, right? However, this is the very simple. Here nothing I have done, because it is a very simple circuit. Simply remember that. So the input side of the transistor is to be further simplified with the help of the Thevenins theorem only. So Thevenins voltage, Thevenins resistance, VB, right, and RB. And afterwards write the input loop equation and bring the relation for IB, and IB is equal to something you should write, and differentiate that IB with respect to IC. Then you will get some value and substitute that value in the standard definition of the stability factor. There you will get this by assuming this particular. This is the assumption that we should take, right? So I hope you understood well, and if so, please do not forget to give your valuable suggestions and feedbacks and comments, and also request you to all to share this information to your friends and colleagues, and so that most of the students community should get the most and maximum benefit of these presentations, right? And your observations and whatever whatever type of your feedback are highly welcome, and they are definitely appreciated, right? So let us finish off this presentation here, and we'll meet in the next subsequent presentation. Till then, have a wonderful day.